Hi, everyone. Thank you for coming to the talk. And as Sean said, anytime you guys spend thinking and learning about evals is time well invested, because not a lot of people spend enough time kind of critically thinking about this problem, and I think it's probably one of the most important problems right now. So let me just kind of give you guys a quick outline of what this talk is going to be about today. So. I'm first going to start from a very obvious question, which is sadly something which needs to be discussed, which is why should you evaluate agents? It's kind of too easy to build a prototype, so this is an important problem to just keep talking about. The next part of the talk will be about this concept of an error cascade and why that is the key problem that you need to be thinking about when it comes to agent reliability. And from there, we'll get into how do we detect cascades, and then finally, we'll get into how do we fix them. So this is going to be the rough outline of the talk. So first, quickly about myself and maybe why I know about this topic. So I started in generative AI in 2021 at Microsoft. We were building code agents with OpenAI using their early codex models. And back then itself, we had a very simple question, which was how do you evaluate a prompt? How do you know it's ready to go to production? And I still think it's been 4 years since that day, and that question hasn't been fully answered. But I realized that this is going to take a while and a lot of research to fully figure out. So then we started a company in late 2022, me and my college roommate, around how do we build good evaluation and observability tooling for agents and RAG-based systems. And with the company itself, it's 2 years old now. We recently raised a new round, and we've been working on distributed tracing and evaluation systems for AI. And we've had the good fortune of working with every company from small 3-person startups to large, thousands of people orgs, Fortune 50s. So let's jump into it. So why should you evaluate agents? I'm just going to preface with a lot of these images are AI generated, so we're already on track. One key kind of intuition that I have around why you should evaluate agents is agents are only valuable if you can leave them on their own to do things. As long as you need to be looking over an agent's shoulder and double checking its work, it's never going to fully, it's not going to cause 100x increase in value or productivity or time in any sense. At best, it could be 2x, 3x, but as long as agents have to be supervised by humans, we're not going to get to a crazy AI world outcome. So the bridge of how do we go from the human in this picture who has to look at so many dials and signals to an autonomous agent which is happily getting the job done is through evals. So that evals is this bridge from the current human in the loop world to the world where AIs are basically working on their own with very little supervision. And I think this is a very tricky problem to think about, but the question is how much accuracy should an agent have before you should feel comfortable letting go of the wheel and letting them take over? And so I just thought I just had this thought experiment, which is if I do some kind of task 3 times a day, so this might be opening a PR, or this might be checking my mail or something like that. At what success rate on that particular task would I feel okay with an agent doing it for me all the time? And I realized basically if the agent has 95% success rate, it would fail once a week to do the task properly. And if it was 99.5% successful, then it would fail once every 2 months. I don't know about you guys, but 95% seems pretty close to my accuracy. I feel I screw up a task once a week. It's not, not like a robot, I guess, or perfect. I mean, robots suck too right now, but, I feel 85% is a helpful intern, which is kind of the state of the art today, where you're not fully letting go of the wheel, but you're basically just watching from afar as cursor makes a lot of changes to your code, kind of a thing. But at least you can, they're at 85% accuracy, they're a helpful intern and someone you can work along with as a sidekick. I like to think of that as Batman and Robin. And 95% is you just, retire from the Justice League and let Superman take over or something. And so the question comes up, which is like, what's the holdup? Why haven't we gotten to a point where agents can fully take over from humans? And here's a thought experiment for you. The telephone game, I'm sure you guys have all played it when you were in kindergarten, where one person would whisper something in one person's ear, and then it would go through 30 people, and at the end, the teacher would ask, what did the last person hear? I guess what happened, right? It was always something completely new and random, and who knows what happened in the middle, and now the trajectory has gone in some weird direction somewhere. And now imagine if AIs did that. That's basically the problem that we run into, which is like, if at the beginning of the task, you're working with an agent, you're like, okay, I want you to go through my mail and find anything that I need to act on. And at the beginning of the agent's work, it's like, yeah, I get it. I understand what I have to do. And then you come in like 3 hours later, and it's doing completely something random. So first things first, I just want to call out this kind of like telephone game is not an accurate representation of a lot of AI applications in the world today. Most of the AI applications that I see being built right now are like deterministic system with sprinkles of AI. Like it's like you're just adding AI in like a particular step within your software-based system, wherever you feel like it's adding some value. So like summarization, NER, structured data extraction, these kind of like single LLM call-based systems are like you can make them pretty reliable and get a lot of value. So don't worry about telephone game if you're building something like that. That's not your concern. You have a lot of methods and a lot of eval methodologies to get those reliable today. But this is what the telephone game would look like. I really want you to pay attention to this chart because this is like what the whole talk is really about, which is if an agent does 10 actions in a row, right? And I think a lot of useful human work requires 10 successful actions in a row. I reflected on this a lot. Like I think most of the tasks that I do during the day require at least a sequence of 10 successful actions. If the agent had 99% accuracy for each action, by the end of 10 actions, it would overall have a 90% success rate. That is still not 95%, which is when I would feel comfortable letting go. So then we're basically left at the 85% where like, okay, cool, I can't let go, so let me get a good intern. And to get a good intern, you need, it's actually 98.3, it's not on the chart here, but basically around 98%. If each action is 98% accurate, after 10 actions, you will reach 82% overall success rate. So this is geometric progression, right? Like each step, there's a huge exponential drop off in terms of the number of agent trajectories which are actually correct. So this is like the main intuition for why multi-step AI or like compound AI systems, which I think a lot of AI systems like 3-4 years out, what I imagine will be like very complex systems. This is the main problem that they're gonna have to work around, which is dealing with the stochasticity that we're introducing over like long sequences and long trajectories. And the state of the art of how do we get around this is just throw a human in the loop. That's basically the state of the art. The human basically steers the wheel. If the agent starts going in a weird direction, the human just comes in and just shifts the direction again. And this is basically how we're like if you might object saying, hey, I still have like multi-step, multiple action sequences working for me today, I would say it's most likely because you're in the loop. So just kind of rehashing the old point, like agents which have to do like more than 10 successful steps in a row have it bad. They need 98.3% accuracy for each step to get to any meaningful point. And I guess open question for everyone in this room, have you seen an LLM which is 98.3% accurate at any task? Any? Okay. So I think we're in a weird world today. I think people are creating like very complicated compound agent systems, LLM systems, but I think they missed this basic probability intuition before they started building them, which is like, okay, let me show you like, so these are like kind of the state-of-the-art LLM applications that are being built today. There are like 3 canonical architectures that I kind of see out there. One is like the while loop agent, which keeps making actions. The other is like a really complex RAG system, which is like spoon feeding context into an LLM after a lot of thought. And then the other is this kind of like multi-agent system with like delegated responsibilities, and you're always trying to like make sure the right agent is doing the right thing. So these two kind of systems are like born out of this need to like not overwhelm the LLM with a lot of context. And the second one, I think, is more built from a need of this while loop system breaks in weird ways. Okay, let's try to make it a little bit more opinionated to like make it more stable. So this is kind of like what I've seen when I see multi-step systems in the world today. And if you trace any of these systems, so like here's a trace from HoneyHive where we took Manus AI, which was like popped off recently. Dude, they generate a lot of tokens. They loop a lot. Like just for answering a very simple question, it had like 20 different LLM steps and it was generating 100,000 tokens. So I want to quickly call out, this is wild. This is not like, it's not a definition of reliability by any means. Like, I think the most impressive agent reliability result that I saw from the last year was this result from METR, where they talked about what is the best predictor of agents' ability to succeed at a task. And they found that it is highly negatively correlated with the time it takes a human to do the task. So in this chart over here, what you'll see, interestingly, is that kind of beyond like the 2-minute, 4-minute mark, like if it takes a person like an hour to do a task, like model success rates are around 20%. And then if you think about like anything that requires a person like a few seconds, so like it's like a few clicks you could imagine, or read a screen and then click a button kind of thing. That stuff agents are getting pretty reliable at. And kind of, keeping in mind that earlier like geometric progression slide, this seems very expected to me. It's like the longer it takes a human to complete a task, the more kind of dependencies need to be like done correctly. But yeah, R squared of 0.83. So I think it's like a significant enough result, at least in my mind, to think about. And this is kind of like a rule of thumb that I go with now whenever I see an agent application, which is if this agent requires like at least 5 steps to be done correctly in sequence, it's probably not reliable. Like it's because I don't see LLMs being 98.3% reliable on any particular like one-step call. So they're probably going to have me human in the loop it. So I think this maybe is like I think already clear to everyone, but I just want to rehash it, which is like now we're kind of going to start thinking about like, okay, what do these cascades look like? What's actually going wrong here? Like I want to now give like color to this problem. So on a high level, what agents need to get right is understand the reward, like understand the task, what you're trying to do, understand the sequence, make sure it plans the right sequence, make sure it does the steps in the sequence correctly, and then finally, if something doesn't go as expected, come up with the new plan correctly. This is kind of like on a basic level. And what goes wrong in practice, it's pretty fun actually watching agents screw up. Like I think just thinking about like autonomous systems, I think something came up in the previous keynote, which is like, the first thing that I've seen agents do is they'll just give up prematurely, right? Like, they'll come up with a nice plan. They'll try doing it. It doesn't work. They're like, hey, human, this is how you do it. Go figure. Like, I can't do it because I can't click this button on the screen for some reason. But here's a plan for you. The second one is if they're really frustrated, and I'm talking about frustrated in an agent sense, I guess, they'll just hallucinate and be like, yeah, I think I did that. And then they'll just move on. Another thing, this is pretty common with coding agents, which is do like tangentially relevant thing. Like, you'll ask it to like fix some part of your code and then it'll take the liberties of refactoring another file. So that's like, it seems like, the agent's like, oh, I think you're asking me to help you write better code. Fourth is like very commonly seen with like more of the while loop agents, which is just keep looping and not do anything. Like they'll just like come onto a browser page and then like they won't be able to click a button and then they'll go up and down. Like they'll just keep looping in the same area without ever asking for help because they don't know when to ask for help. And fifth is a recent one. I think reasoning models are making this pretty common now, which is gaslight humans. which is like Claude will go and like change the test sometimes if you're asking it like pass a test, like hard code a result in there. Sometimes they'll just be like, if they're like trying to, like something I've seen, like booking a reservation, even if they don't book the reservation, because they have so much conviction in their plan, they're like, I think I booked it. And then you have to like go in and check like, wait, did he actually book it? And then like, no, it's not. So yeah, that's another kind of failure mode I've seen with autonomous systems. So of course, all of these like failure modes aren't too bad if you have a human in the loop. So that's kind of the last line I've put here, which is if your system is not autonomous and there's a human in the loop, then they'll just ask you to like restore checkpoint and retry. Like that's state of the art. I don't know if you guys can see this. I wanted to show you guys some agents in action. So forgive me for making it kind of a bloody demo, but this is Doom, and this is like basically 4 of the best models trying to play Doom. And it's, by the way, in real time. They slowed down the game emulator so that it syncs with the reasoning time. I don't know if you saw Flash, Gemini Flash, like completely screw up that trajectory. Like I'll show you what happened. So the other reasoning models like, yeah, like Foro and Sonnet are just killing it, right? Like they know it, they can see from afar when the bots are coming and then they're like shooting them like instantly. Flash is just confused, dude. Like it's just like roaming around like, what is going on? And then like it goes off in a random direction, not even down the right hall. And then it gets stuck in a corner and then it dies. So I really wanted to show you guys this because I don't want people to think of AI as software and like all LLMs behave the same. They're pretty unique. Like I just wanted to show you this. Like this is like a mental model I live by, which is every AI agent is a snowflake. Like every LLM is different. They all have weird capabilities. They all have been trained in different ways. And like whatever domain that they've been applied into, that's probably a domain that they weren't trained against. So, you know, in the kind of AGI dream, you would imagine that, you know, all the models would converge and work in all domains and be perfectly autonomous everywhere. But that's really not the case. Like LLMs aren't AGI. They all have weird capability quirks and unique quirks. So yeah, like you do not want to just like drop and replace models, especially in more autonomous systems. Because yeah, they all, like if you saw from that Doom video, like they had very, very different approaches to the same environment and the same problem. So and that's why I really wanted you to show you that video because yeah, I just wanted to get this point across, which is agents are snowflakes. They're not like all the same. It's not kind of like our old world that we're used to. And the reason I also wanted to talk about this is because this is like a very important slide that I think Richard Sutton released recently, where he was talking about, so of course Richard Sutton of the Bitter Lesson fame, where you know he talks a lot about like search and learning and like basically like the least sophisticated approaches which scaled compute very well won in the end. Like that was the bitter lesson of AI. And he came up with this slide talking about like, okay, how will agents be built and how will AI be improved in the future? And it's very interesting the way he talks about it, which is basically over 2018 to 2023, we've capped out as much human data that we can train on as much as we can. Like we're still collecting a lot, but I think it's, you know, kind of going into 2024 and beyond, the way that AI systems will improve will be through understanding their production trajectories and their experience, kind of to speak of, which is more to do with like finding, like basically throwing them in the wild because they have enough pre-trained abilities to like get around essentially. And then seeing in this kind of wild production open-ended scenarios, them getting to like working trajectories and like using those working trajectories to like do RL over. And so his point is that the use of RL is just going to increase like over like a lot over time, essentially because we are going to like, yeah, like when you think about superhuman intelligence and like getting like, improving that, a lot of it will be based on like finding trajectories from the wild and then distilling over those and like searching over them better. And how do you do this as an AI engineer? I really want to make this point, and I think this point will never die, which is read your logs. It's again, like I think people don't get the point that agents are snowflakes. They have this like weird intuition that their LLM is like perfect in some way, and like, oh, I don't need to read my logs, like it'll figure everything out. Like, no, dude, no. Like, it will not. Like, we're still in like we're not AGI right now, no AGI. Like, sorry, like, you need to read your logs for that reason. Like, your model is not going to generalize over the entire domain. It's not going to be able to handle every input perfectly. So that's why you have to keep reading your logs, because your production scenarios will show you and teach you a lot more about how your model works than whatever docs you're reading from Google or OpenAI. And I wanted to show you this slide, from Rahul from RAMP at the AI Engineer Summit, which I thought this was a very, very important point that he made, which is people might, like basically in a world where you don't have AGI, different applications are going to have different levels of autonomy, depending on how, my intuition is like, depending on how much, how well an AI already understands a particular domain, you can give it more and more autonomy within it versus less. And so the spectrum that has been created because we don't have AGI is basically over-engineered code. This is like the complex RAG, like text-to-SQL pipelines that you see hanging around, where they have like very, very opinionated like abstractions and modules trying to get the AI to do something very specific. And I feel like it's very brittle. It's hard to maintain. It doesn't generalize very well in production, but it works within a very constrained setting. The other is like a constrained agent. This is more like an agent now like, the system is not fully opinionated. It's like more like less opinionated, but it's very fixed in its schema. So like what input and output you want, but you're giving it a little bit more freedom in how to get there. But this system like basically struggles with edge cases essentially because it doesn't have like a good external validator or verifier. So it's the chances of hallucination are pretty high. And then the final is like a flexible agent which has its own shell environment and like an external verifier to work against, and like basically can generate code on the fly to get the task done. And these agents will basically be like super adaptable. They'll work across like very wide variety of inputs very easily. And the main point here is very similar to Richard Sutton's point, which is the more compute your system can harness, the more robust it will be in like more production environments. Like it'll be able to handle more edge cases more neatly. And yeah, I just wanted to show you again, like that's basically like what this kind of diagram represents to me, which is like, that's your brittle text to SQL kind of pipeline. This is like your completely open-ended agent just looping on its own. And then you have like a slightly more constrained multi-agent system, which is trying to be more opinionated about how the tasks will get done and how the states will be managed. And like there's a whole debate going on Twitter right now between Harrison and OpenAI around like, I think how opinionated or less opinionated your framework needs to be if you're building an agent. The way I kind of think of it is like, how many independent variables does the AI have to play with, and like how many constraints does it need to satisfy to solve a particular problem? And so basically more complex and more difficult tasks require, in my opinion, a less opinionated agent which scales with compute very beautifully. And like a less complex and low difficulty task where like the domain is constrained, the input space is very constrained, there's fewer independent variables to work with, you can get away with we can get away with a more opinionated system which is like very unique to that particular domain. And the reason this is important to think about, and now we're going to get back to error cascades very quickly, which is the way that you feel the error cascade and you see the error cascade is dependent on the level of autonomy that you're assigning to your system. Basically, the more autonomous your AI system gets, the more you're relying on the LLM to handle the control flow and make the right decisions for getting the task done. And the more you're introducing hidden failure modes and the more you're introducing like those compounding errors into the execution of your system. So basically like the super constrained systems where you're like being very, very opinionated on how the inputs and outputs should look, you want to make sure that the steps and the modules in your agent are like evaluated and tested very well. The less opinionated your orchestration gets, the more basically you're reliant on running evaluations over the trajectories and the tokens that are there in the agent's logs, and less so in the code and like the modules that you've defined. Because essentially you're like letting go of the wheel, if you can feel the analogy, which is like the more you let go of the wheel, the more you need to look into the logs and see what the actual failure modes that are being introduced are. And the more opinionated you make your system and the more you try to constrain your LLM, the more you have to basically test the modules and you're kind of thinking in that complex RAG case. Like I would add like a, evaluation module for the table agent. I would add an evaluation module for the column selection agent. Like in that more opinionated kind of diagram in the right, like my evaluation strategy would be very linked to my orchestration strategy. Whereas in a more unconstrained system, like, dude, what if I can't evaluate anything here? Like, what's action? Like it depends on production. It's not known before it's actually executed. And here's like an example. I think Hex already gave a talk today called Failure is a Funnel. I think it's kind of similar concept that I'm discussing here, which is like, he basically is building this text to SQL pipeline for Hex in their product. And the way that they're evaluating how well the agent does is based on like very well-defined failure modes, which is very specific to that particular task. And you can see the exponential drop-off, right? Like you see the first step has a certain failure rate, the third step has a certain failure rate. This solution is like less than 50% success rate. So like any failures early in the pipeline just geometrically explode down. So this is like a very nice example of an error cascade. And also why like getting a multi-step compound agent reliable is a very hard task right now. Because each one of these things actually need to work for, like I want that intern, man, like 85% success rate, like not even happening right now. And then here's like a more unconstrained agent. Here's like an example of a browser agent and what a failure mode might look like there. So I cannot create a neat graph like this because it's completely unconstrained. Like people might be using this agent for booking restaurants, for writing their emails and, opening a GitHub PR. Like this is a unconstrained autonomous agent. This is a browser agent. So like the possible set of tasks and domains that it's like being evaluated over is too wide. But still, like basically I'll look over the logs. Here's like an example, which is pretty funny. This is like booking a reservation on OpenTable. The LLM starts by going to the wrong restaurant. That's like the first failure mode right there. But then it realizes on the wrong page. It corrects the plan. Then it goes to the right restaurant. Then it clicks on the wrong date. But it thankfully realizes it's selected the wrong date. And then it selects the right date, selects the right seat, and then reserves the place. This is a wild trajectory, but this is pretty representative of what autonomous agents today feel like. Like they'll just make like weird random decisions. I'm sure you've seen Claude and Cursor do this. Like it'll like try some weird change and then be like, oh, that didn't work. And then it'll come up with something new and then be like, that's what happened. And then it'll like fix its trajectory and move on. And so error cascades in autonomous systems are like trickier to detect, but they're definitely there. Like each one of these steps is like dependent on the previous step in order for you to get to it. So if the agent never got to the right restaurant, it would never get to the form itself. So there's like the cascade kind of built into this task, but it's luckily able to get through it. So now let's talk about how do you detect error cascades and how do you fix them, because this is the practical part of the talk. I feel like I've spent too much time on the earlier stuff, but still I feel like it's important to get a good intuition for this and like think about the cascades in your system, because your logs are hiding all this information from you. Don't look at your code too much. So how did Hex see this cascade? Like the way that I think of this slide is like, how should you read your logs? Like I think this is stuff that Hamel already talks about, but I do want to repeat it because it's important, which is you have to create a really nice visualization UI for your logs. Like make it fun and friendly for people on the team to go through the logs. If they find it boring and they find it tedious, your agent's never going to work. Then the next thing is like, after going through a bunch of the logs, try to just, in an unsupervised way, like make notes of the kinds of weird failures that you're seeing. And then once you've kind of found the failures, rank them in the base of their criticality, and then run an evaluator agent over your logs, or LLM as a judge, let's say, and then basically make sure that the LLM is detecting the failure in the way that you want it to. And then after you feel like you're happy with the evaluator's like kind of automated checks, then just see like aggregate statistics for the different kinds of failures that you're seeing in the logs. So really think of evaluators as like your slice into what's happening in production and what's happening in your logs. So you want to basically keep reading your logs and find like different ways to look into your logs, and think of your evaluators as like those perspectives into the log and trying to find and capture those different features. I will say this methodology is actually quite different for reading autonomous agent logs. Like the previous methodology works really well for like non-autonomous, very complex, like complex RAG type systems. But for autonomous agents, dude, they generate a lot of tokens, like a lot of tokens. It's like you can't just do naive like LLM as a judge on autonomous agents logs, just because like they generate a ton of tokens. So the main tricky piece in basically doing those automated evaluator checks for autonomous agents is context management. Like you have to figure out different ways of distilling the log context into a more sizable, like into a manageable chunk for the evaluators to like understand and like measure over. I'll just show you a practical example of this. So Anthropic, the way that they evaluate their computer use agent is this kind of a pipeline. I don't know if this hasn't been discussed really enough in the literature a lot, but I think it's quite insightful, which is they obviously had the same problem of like computer use agent trajectories are like very long and very heavy. They have images, they have a lot of text and reasoning built into it. How do you like extract features out of that at scale and try to understand where your computer use agent is going wrong? So basically they do like per interaction summaries. So for every exchange that the agent does, every action that it makes, they're summarizing that into what was the goal, what was the outcome, and what were the steps. So they've kind of taken like the very long reasoning context and boiled it down to like 3-4 points. They do that for each and every single action. Then they will have a summarizer on top of that, which will say what was the overall like interaction summary, what happened in this general sequence of interactions. That goes to usage summary, which is then aggregated across all the trajectories. So this is a real world example of how you do evaluations for autonomous agent logs. Basically the weird opinionated part here is that you need to do a lot more context management, and you need to distill the token down more carefully because there's just too many tokens to go through. And like this is an example of like a trajectory evaluator that one of our customers built, which is like, so this kind of an evaluator is like aggregating across all the actions within the trajectory. This one is a per action evaluator. So at each step in the agent's trajectory, there is another LLM which is looking at the history of the states that came before, and then makes like a relative judgment of like whether the action that's being selected at this point is relatively the best one or not. And then they actually distilled this LLM critic from their production data and put it back into production as like a re-ranker for all their actions. And that actually improved their agent accuracy a lot. So that's kind of one way in which you can use the failure modes to go back to production and improve performance. And then this evaluator is actually the most important for autonomous agents, which is the success evaluator, like whether it completed the task successfully or not. Ideally, this should be deterministic and not reliant on another LLM to score. But many of the tasks that people have agents do are like a little bit open-ended and subjective. So yeah, like this, if you were stack ranking priority for like evaluating agents, I would spend a lot of time building a really good success evaluator, which looks at the end state of the environment after the agent is done with its trajectory, and then evaluates the environment to see whether the objective was achieved or not. And does not take the trajectory, do not take the original model's tokens into account, because you don't want that to bias your other model. So this is the success evaluator, then you have the per step evaluator, and then you have the full trajectory evaluator. This is the kind of ways you have to think about for autonomous agents, how to evaluate them. it's very different from RAG systems and the other ones. And yeah, I added some examples for like possible per step evaluators. I won't go through these. But what I do want to call out is trajectory and success evaluators are super specific to your domain. Do not just use a templated success evaluator or a templated trajectory evaluator. It's, again, remember what I said. Every AI agent is a snowflake. Like, do not forget that principle. Like, it's very, the way you evaluate your trajectory is specific to your domain. It's specific to your model. And the way that you evaluate success of the agent is obviously specific only to your domain. But yeah, do not use a success evaluator from one domain in another. Like, that's totally owned by you, and you should be thinking about it. Some of the per step evaluators are fine. Like, you can use some templated metrics for that. That's perfectly valid. So I think hopefully I kind of rushed through that piece, but hopefully you've gained somewhat of an intuition for what error cascade means. How do you actually like go through your logs to discover them? How does that differ for like discovering error cascades in autonomous versus non-autonomous systems are quite different. And now coming to like how to fix them. So I think for autonomous agents, believe it or not, they're actually simpler to build than non-autonomous systems. Because I do want to go back to the bitter lesson, which is you want a very unopinionated orchestration strategy if your agent is supposed to be autonomous. Because the more opinionated you make its orchestration, the more fragile you make it. And so what you, in practice, end up having to do, this is what we've seen from our customers, is you read your working trajectory data and you start constraining the possible set of queries that your agent is expected to handle based on where you're seeing it working in production. That's one way. The other is basically use clustering or more like human supervision strategies to like build detectors for those failures. And then the way you can use those detectors is either as test time search or as offline RL. So once you have the failure modes and the cascade figured out for your agent, you can set up evaluators and create data sets for RL for them. And you can do online RL or offline RL using the evaluators that you discover. And that's how you would improve an autonomous system and fix these error cascades. For non-autonomous systems with complex RAG, it's more hacky. You have to like play around with the prompt criteria and like add a new LLM step sometimes and like reduce the context management. Sometimes you have to like try different models because the model doesn't have the capability. And if all else fails, just throw in your evaluator as a verifier in production and just like, don't go to the next step if the evaluator is failing. And so, yeah, finally putting it all together, first things first, errors compound rapidly in multi-step systems. There's a geometric progression of errors. Second, every AI agent is a snowflake, so read your logs. And third, based on the autonomy level, there's different ways of reading your logs because there's a lot more tokens to go through for more autonomous systems. Fourth, map out the error cascades in a supervised or unsupervised way. Anthropic has a lot of interesting papers on doing it in an unsupervised way. And then supervised way is just like ask your domain expert to like say what they don't like. And then finally, prioritize the fixes that you're making in your orchestration based on the limiting step in the geometric explosion. Whichever step is causing the highest failure rate, just start by improving that once you have the cascade figured out. So yeah, this is an AI agent riding off into the sunset. Yeah. Thank you.